Hi guys, and today let's prove the basic derivatives without limits. And so the reason we want to do that is because proving derivatives with limits, using the definition of the derivative in terms of limits is very difficult and very long. So there's a much easier way to do this, and I'm going to show you. So first of all, let's start with the derivative of x to the power of a, so a being a constant. So now, how do we actually find it? Well, we're going to use, actually, in order to prove all those derivatives, we're going to use a knowledge of only two derivatives. And so one is, we're going to use the fact that e to the power of x prime is equal to e to the x. Okay, we're going to use that. And so if you want to prove that, I guess, well, you have to use the limits. But so suppose we already proved it, so we know it. And then another one is that the power of, the derivative of ln x is equal to 1 over x. So in order to prove that, you can easily prove it. I already showed it in another video. Anyway, we're going to use this knowledge. We're going to use this knowledge in order to prove all the others. Okay, so let's start from x to the power of a. Well, we can actually express this as e to the ln of x to the power of a, right? Because you know that any number is equal to e to the ln of that number. You should know that property. And now, if we, you see this a, we can actually take that a and put it over here, because that is one of the properties of the logarithm. And so what we get is actually, let me just put that aside a little bit. What we get is actually the derivative of e to some power. And so how do we deal with this? Well, you know that it's going to be that same thing, because it doesn't change. E to the something doesn't change, so it's going to be e to the a times ln x. But we also have to multiply it by the derivative of the inside function, so it's going to be the derivative of a ln x. Now, if you notice, this thing over here, it's actually the original thing, right? It's the original thing. It's x to the power of a. Okay? This thing over here is actually equal to x to the power of a, because that's the original thing. So we're going to write x to the power of a. Now, how do we find the derivative of a ln x? Well, a is just a constant. It's just a constant, so we just put it in front. Sorry, I forgot the prime. Okay, so we just put it in front because it's a constant. So times a. And now, what is the derivative of ln x? Well, that is 1 over x, right? And so as a result, you see we got 1 over x, so that's a times x to the power of a, and times x to the power of minus 1, right? And since it's x to the power of a times x to the power of minus 1, we just do it a minus 1. So the final answer is a times x to the power of a minus 1. And that is the answer. So as you can see, it's like pretty fast. It doesn't require you to use any limits, which is much easier. Okay, great. Now, let's do the second one. This time, let's do a to the power of x, which is a little bit more interesting. a to the power of x prime. Now, we do exactly the same trick. So we rewrite it as e to the power of ln a to the power of x. And we do exactly the same thing, so we and that all prime, and so we just put x, this little guy here, we move it over here just like last time, and so we get the same thing, right? So because e to the power of something prime is that same thing, so it's going to be x ln a. And then but we also have to multiply by the derivative of the inside function, which, so it's going to be times the derivative of x ln a derivative. Now, if you pay attention, of course, this thing right here, just like last time, it's actually the original thing, right? It's the original thing. It equals a to the power of x. This thing. So we just write a to the power of x times, now what is the derivative of x ln a? Well, don't panic, because ln a is just a constant, right? Because a is a constant. So what you do really is you just put ln a, just take this ln a and put it in front, because it's a constant. And so what you're left with is just the derivative of x, and the derivative of x is just 1, which is great. So all you get is times ln a times 1, and you don't have to write times 1. So that is the final answer. The derivative of a to the x is equal to a to the x times ln a. Very simple. Now, let's try one more. And this time we're going to do the product rule. So we got u times v prime. Now, how do we prove this? Well, now if you try to prove that with the limits, it's like pretty messy. So this way is much easier. So we do the same thing. We just express this as e to the ln of uv. Okay, you do the exact same thing. And now the cool thing here is that ln of the product is actually equal to the sum of logarithms. So it equals to ln u plus ln v. And this is awesome because we basically turned a multiplication into a simple plus sign, which is great. You'll see why it's such a good thing. So that prime, and so what it equals to, now e to the something prime is equal to the original thing, and remember the original thing is actually just uv. So let's just write uv because it's the original thing, okay? Now times the derivative of ln u plus ln v, and that's going to be the derivative of that. Now this is awesome, right? Because it's the derivative of sum of something, and so the derivative of sum, you just find the derivatives one by one, and so it's just uv times, now the derivative of what is the derivative of ln u? Well, it's just 1 over u, but then don't forget that u is a function of x, right? So you actually also have to multiply by the derivative of u, because it's u is a function of x. And then plus, and then you do the same thing. So what is the derivative of ln v? Well, that's 1 over v, but then since v is a function, you also have to multiply by the derivative of v. And now you just factor in, and you notice that if we put uv here, then here and here u is going to disappear, and at the first term we're going to have v u prime, and then plus, and here v's are going to cancel out, and we're going to have u v prime. That's it. That's the answer, and we have proved the product rule, and that is so much easier than using the limits. And now finally, let's prove the quotient rule as well, using the same technique. Now, we're gonna have, let me draw a line here. So this technique, as you can see, is very, very powerful. Okay, so it's going to be u over v prime. Now, how do we prove this? Well, we do the same thing, so it's going to be e to the ln of u over v prime, and that is, well, you should know that according to the properties of logarithm of something divided by something is actually equal to, well, anyway, ln of u over v is equal to ln u minus ln v. So that is a property of the logarithm, which you should know if you're doing calculus. So that prime, and so that equals the original thing as we did before. So there, and notice that the original thing is actually u over v. Okay, so I'm not going to write e to this because I'm lazy. So I'm just going to write u over v because that's the original thing, times, but again, times the derivative of the inside function, right? And so the derivative, so we're going to have ln u minus ln v, and that and the derivative of that. So that equals to u over v times, okay, and it's, as you can see, it's very similar. It's just the only difference from the last one is that we have u divided by v instead of multiplied by v. But then, and we also have a minus, so that's like the only difference. So we're gonna have 1 over u times u prime minus 1 over v times v prime. Okay, and now if we factor that in, you're gonna notice that, well, let's just write it. So u times u prime divided by v times u minus uv prime divided by v squared. Now you notice that this and this cancel out, this u and this u cancel out, and now if you just do times v on both sides, okay, you just multiply by v on both sides, you're gonna get u prime v minus uv prime, all of that over v squared, and we are done. We're done. So as you can see, it's a very, very easy, very elegant, very fast proof of the basic derivatives. Okay, thanks for watching.